All right, so today what we're going to do is give you a whole bunch of properties from algebra, which means we're going to start doing proofs. But we're going to start with what you're familiar with. We'll start with algebraic equations to solve. So we're going to be talking about properties from algebra. These are all theorem cards because we use these in our proofs. Though, truly, we do use vocab cards also in proofs. And this comes out of lesson 2-2, and today's date is the 19th of September. What's up, Kanoa? You're trying to show him a picture on your phone?
Yeah.
And you have your phone in your pocket and it's on, even though that's against school rules? Do you realize I am recording this for posterity? Phone off and go put it in your backpack. And don't show him a picture again. So we're going to break properties into the ones you're familiar with, and those are the ones that dealt with equality because they deal with equations. Okay? So we've got, now this is not a vocab word, so I'll box it. It's just a general heading for all of these. Okay, so we have the addition property of equality. And basically what the addition property says, and we used it a ton last year when we were solving equations, is you could add the same thing to both sides, and it doesn't affect the answer you're going to get. It's not like you're changing. As long as you treat each side the same, that's fine. Now, when I write down those words, I'm going to write it down in an algebraic fashion. And the first version, I'll do this in a color. If A equals B, then, then A plus C equals B plus C. So basically I'm adding the same value C to both sides. And that, again, we did that a ton. Now, it also has a second case. And the second case is the one that tends to show up in proofs. Not this first case, but the second case. So I'll do him in a different color. So if we have two equations, A equals B and C equals D, then A plus C equals B plus D. And where those values came from is I took the left terms and added them together to get the A plus C. And I took the right terms, added them together for the right side of the equation. Andy, you need to be taking notes. So it's super important that you understand this second idea behind the addition property of equality, because again, this is one that shows up over and over and over and over again. Not the first one, you did that in algebra class, but in geometry it's the second one. That's your addition property of equality. All right, next one. Subtraction property of equality. Now I'll show you when we do proofs how I abbreviate, and I will accept your abbreviations as long as they're reasonable. And this one kind of goes back to that first example, and it just says if A equals B, then A minus C equals B minus C. So I'm maintaining that equality when I'm doing the same math to both sides. And then we have the multiplication property of equality. And that one says if A equals B, then the product AC equals the product of BC. And in other words, what you did a ton of last year, if I multiply both sides of the equation by the same thing, I'm not changing the values at all, okay? I'm just increasing them the same amount. And guess what's coming next? Yeah. Am I ready? Can I move?
Yeah.
We good? Michael, you ready? Okay, good. So now we're up to division property of equality. And this one says if A equals B, so I have some sort of equation. Oh, sorry, I have to make a stipulation. And C does not equal 0, then A divided by C equals B divided by C. And why did I have to make that stipulation? Why did I have to specifically say C could not equal 0? Okay, let's see, somebody I haven't talked to. Flint.
Not divided by 0.
Mathematically, the only thing you will never be able to do is to divide by 0. Because that says, I want you to take something and break it into 0 groups with an even amount in each group. Okay, by definition, you have one group. You can't make one group be no groups, so that's why we mathematically can't do this. And this was an interesting concept that came up in the other two classes. We're in the real number system, and you will learn about the imaginary system, not in this class, but in another one. But in the real number system, you have rational numbers and irrational numbers. And so we were trying to figure out if I took a number and divided by 0, what kind of number would it be? And so we were using the closure property. If I took all real numbers, is it closed for each of the operations? Meaning, if I did any kind of math with a number, would the answer be in that same group of numbers? Now, remember, real numbers is everything you've studied, right? So is there any way to add two numbers that you've studied and get an answer that's not in the group of numbers that you've studied? And the answer is no. It's always going to be there. So we say that's closed for addition. And then the same thing happens for subtraction. There's no way to subtract any two numbers you've ever learned about and get an answer that's not in the group of numbers that you've learned about. So it's closed for subtraction. Same thing for multiplication. You can multiply any two numbers that you've studied throughout your whole life, and the answer you get will be in that group of numbers. So it's closed for multiplication. And then we thought, what in division if you divide by 0? Does that mean it's not closed for division? So Mr. Johnson and I got posed that question. We were like, let me think about this. So we went and did some research. And technically, we still say division is closed for real numbers because you can't get an answer when you divide by 0 because you can't do the operation. So they say it's kind of, there's no answer to say it's not in the group or out of the group because there is no answer to get. So that's why they still say that it's closed for division with real numbers, because that case of dividing by 0 doesn't result in getting an answer because it's mathematically impossible to do. It's a little tricky there. Mikey?
Are irrational numbers real numbers?
Yes.
So what happens if you multiply two irrational numbers?
You just get a nice bigger irrational number, unless it's something like radical 2 times radical 8.
Yeah.
What would you get there?
Well, but then like...
Nope, answer my question. Radical 2 times radical 8 is?
Oh, yeah. 16.
Radical 16, which equals 4. So there is a possibility that when you multiply two irrationals, you get something that just keeps going on forever, it doesn't repeat, nothing like that. Or you could end up getting a rational number. The only other option we have for numbers is imaginary. And imaginary means we get a negative number under the square root. So we don't study those at this point. And there's no way to multiply radical 2 and radical 7 and get negative radical 14. It's not possible. So at this point, we can't do that. But we could get a rational number when we multiply two irrationals.
Alright,
Okay.
because I was thinking like you could have multiplied a simplified form, but then you could just multiply before. Like you could multiply the radical 2, but you couldn't multiply like 1 point.
Right, because we are only doing approximations of all square roots. And that's the reason why we can't say this is an irrational number. No, this is a representation of a rational number rounded. Okay? All right, good questions. All right, so next we're going to get into things that I talked about in my class that I knew were going to come up, and this is something you've used so much. And this is substitution property of equality. Oops. I'm just going to say prop. Oops, go back. And substitution says this. If A equals B, so we have an equation, then either A or B may be substituted for the other in any equation or inequality. Okay? So if I have two things that have the same value, then I can use either one in another problem. Okay, that's still dealing with those two values. Brooke. Oh, I did not get all the letters. You're right. Substitution. There we go. Better. Okay. Now, here's the thing I need you guys to hear loud and clearly. What symbol did you see between the A and the B? What does equals deal with? Deals with, Dakota?
Equations.
It deals with equations, and it deals with measures. It deals with numbers. It doesn't deal with objects. That's going to come into play when we're doing our proofs. This property will not be allowed to be used anytime we substitute something in because it depends on what the substitution problem looks like. All right, another one is the reflexive property. Of equality. And this one seems like a really silly one, but we actually used it all the time in algebra. We just didn't think about it. We're going to use it a ton in geometry. It's one of the most important ones where we're saying something is equal to itself. And where that showed up is when we were doing the actual subtraction in a equation. We were saying we're going to subtract this number equally from this side. So it showed up every time we were doing subtraction property, addition property, multiplication property. We had that reflexive property going on. Again, one of the key properties that we're going to be using in this class. And then we have the symmetric property of equality. We used this a ton last year. This is the one that basically says if A equals B, so if we have this equation, then B equals A. And if you think about it, let's say you had solved out a math problem and you got 17 equals X. You would use the symmetric property to write the answer appropriately, and you would say X equals 17. That's all the symmetric property boils down to. But it's really important because the one thing in proofs is you got to keep things lined up exactly the way that you want the answer to look like. Otherwise, your answer is wrong. Okay? Rachel?
Is it symmetry or symmetric?
It's, symmetric. There I go again. Okay. Symmetric property of equality. All right. Then we've got one more, or two more actually, for equality. So let's go over to the next slide. And we've got the transitive property. Of equality. And this one I really like, and we do use this quite often. It says if A equals B and B equals C, notice there's an overlap of B, then it says you can conclude that A equals C. And we use that a ton throughout the year. Okay? And then the last one of equality would be the distributive property. Oops. And that one states if A, we have this, then we can also look at it as the product AB plus the product AC. Okay, so we can remove parentheses using the distributive property. We can factor using the distributive property. We can collect like terms through the distributive property. All right, so those are all the properties of congruence. Now, 3 of these properties can also overlap and be used with objects. So now this next category is, properties of congruence. So I'm going to actually change colors altogether. So that's not a vocab card. And again, I'm going to put this word next to it, and I'm going to use the word objects. So in this one, we're going to be talking about angles being congruent, segments being congruent. We're no longer going to talk about their measures. We're going to talk about their congruence. So the first property is going to be the reflexive property of congruence. Now it looks like the reflexive property of equality, except for you're going to see an object, not a number or a single variable. So we have a segment, DE is congruent to itself. And we would say an angle, like D, would be congruent to itself. Okay? Very important. That is no longer numbers that we'd be using. We've got the symmetric property of congruence. And that one says if we have segment DE being congruent to segment FG, then we also know that segment FG is congruent to segment DE. Again, order is extraordinarily important when we're doing any kind of proof. And then we can do the same thing with angles. If angle D is congruent to angle E, then angle E is congruent to angle D. So very, very important idea. Cassie?
Can you slow down a little bit?
Okay, I am going kind of slow. You should see me when I'm going fast. Over half of you know what that's like. John. Yeah, anywhere that you can find an open seat next to Rachel would be probably a good view, or next to Kelsey as well. always have to crack up at the people who decide to sit in the back of the class who know that they have a problem seeing.
No, I think he came late and that was the last week. The blue is a bit late for him to see. Black and green and red.
We have color issue. Are you colorblind?
No.
No.
Oh, it's just like
Okay. All right, we've got one more of the congruence properties, and that's it. And then we'll do a proof. Bum, bum, bum. Okay, Cassie, you ready?
Yeah.
Okay. Looks like John might be it. Tell me when you're ready, John. All right, so the last is the transitive property of congruence. Which says if a segment DE is congruent to segment FG and segment FG is congruent to segment JK, then, because we have an overlap of segment FG, we can say that segment DE is congruent to segment JK. The same thing would be true with angles. If angle D is congruent to angle E, and angle E is congruent to angle F. Because angle E overlaps, we've got then angle D is congruent to angle F. So another way to kind of write this, just to get an idea of it, angle D congruent to angle E congruent to angle F. Because of the overlap, the guys that are outside would also be congruent to each other. Okay. So that does it for the properties that you need to write down. So we use these properties to help us justify the steps that we take. So I want to make sure I have enough room here, so I'm going to go to another screen. Is everybody ready to move? Oh. Mikey, you good? Okay. So here's our next guide. We've got, this is our direction. Solve 3x equals 6 minus 1/2 x. And justify each step. When we do a proof, we're going to do what I like to call two-column proofs, and we'll get into this a little bit more. You're going to create something that looks like a T-chart. On the left side, you're going to write S, and that stands for statement. So these are facts. Oops. Well, they're supposed to be facts. Some people don't always write the truth. And then on the other side is R, and R stands for reason. What is the reason you said each statement? Now, when I do a proof, I number my statement and my reason the same number, and they need to be on the same level as each other. So what we do is we start with what they gave us, and pretty much every single proof starts the same way. And we call this step given, because it was given to you, that equation. right. Now, we have a lot of ways mathematically to solve this problem. So what's a suggestion into how to solve this problem? What would be step 1? Okay, Rachel E.
Add 1/2 x to both sides.
Okay, so what she's doing is she would get 3x plus 1/2 x equals 6. Notice that in algebra we would show all of that. In geometry we don't always. We show the result of doing the math. Now what allowed me to do it? We have addition, property of equality. Okay, now what? Aiden. Okay, so technically what math am I doing? And I'm going to do this a different way in terms of 3.5x. We wouldn't normally write it as 3.5. How would we write it?
7 over 2x.
Yeah. We would say 7 over 2x equals 6. Now, of the properties we talked about, which one did I just utilize? It's not really listed out in terms of this idea, but I did mention it orally. Rachel Lee? Nope. That's not a property. Brooke? Nope. I would have switched things.
Addition closure.
Nope. We don't have an addition closure property. Nope. Addition property says I do the same thing on both sides, the equal sign. You're just adding on one side. That's not addition property.
Selecting like terms.
Which is not a property, but what property is it? Blake M? Nope. Because in that case, I didn't say this equals this itself. Drake P?
Substitution.
No. Oh my goodness. Ladies and gentlemen, distributive property allows you to remove parentheses. It allows you to factor. It allows you to collect like terms. So here's technically, I'll show you why. Prop of equality. Here's what that just said. We factored out the x. And we did the math in our heads. That adding 3 to 1/2 is not addition property of equality. That simply is adding the same thing to both sides of the equal sign. So that is the distributive property of equality. Okay, Mikey.
Can we abbreviate like we did under the reasons like on our tests?
Basically what I'm showing you are the abbreviations.
So like can we use them on tests?
Yes. All right, what would be the next step? Sarah.
Or times both sides by 2 over 7.
Okay, so I'd multiply both sides by 2 over 7, getting 12/7. So that would be the multiplication property of equality. So notice what's missing, all the work. Now, does that mean you get to not show work when you're doing algebraic problems on your tests and quizzes and homework? No. This is only true in proofs.